Okay, so this is the last topic of AP Statistics. It's called Inference for Regression. So we're going to go ahead and going back to our knowledge of inference and our knowledge of regression topics together. And let me give you kind of an example here that might help us out to start. So suppose we have a bivariate data that describes a sample. Okay, so two variable data. So maybe the variables are height and weight. So each individual is described by height and weight. So what we have is, let's say it's 20 people, okay, and each individual has a height and a weight, and we run linear regression and we find that height hat equals 10 plus 2 times weight. Okay, so don't worry about units or anything else. This is just to give us a sense. Our sample size is 20. So the first question is, how do we measure how well the line fits the data? Okay. That's our first question. Now, the numerical measure for how well the line fits the data, the line that we have, is r squared. Okay, that's the measure that says if it's, let's say, it's 70%, then it gives us a sense of how good a fit the line is for the data that we have. But the unanswered question, this is something that I think is a little tricky to kind of get your head around first, but I think it makes a lot of sense, is how do we measure how that line fits the population of all people? This is only 20 people. Okay, r squared says that for these 20 people, the line describes the relationship pretty well, 70%. Okay, that's what it says. But we don't have a sense yet of how this line might apply to all people. It's only really talking about how well it fits the data we have. So for instance, if you have a sample of 20 people, but you're really interested in a larger population of people, this r squared only tells you how well it fits your sample. Now we want to figure out a sense of, well, how does the line describe the population of all people? Okay, so this unanswered question is what we're trying to get at here. Let's talk about some more specific particulars. So first of all, we're going to start with a set of data. Okay, this is a data set from the textbook, and what it's talking about is the amount of crying a baby does versus their IQ. Okay, so there appears to be some kind of positive relationship in our data set of 38. In this case, n is 38. There appears to be a relationship between the two. Now, I put this in the calculator, and I found out that IQ hat, I should say, equals 91.3 plus 1.49 times the cry count. Okay, and that's an r squared of 0.207. Now, that's not a very strong fit, okay, for the data, but it's a positive relationship, right? The slope is positive. Now, so this gives us a sense that, okay, well, we can use this line to describe a relationship between the cry count and the IQ of these babies. It may not be a perfectly strong relationship, but we can definitely say there is a relationship, okay? That is to say that as we move to the right, on average, we move up by 1.49 IQ. So for every increase in cry count, we get an increase of IQ by about 1.49. Again, not terribly predictive, but predictive. Okay. So this line fits the data for these 38 babies. What about the line that best fits the entire population? Okay, so let's talk about that. Now here are the conditions for inference for regression. Okay, so this is what we're trying to do. We're trying to figure out how well the line fits the entire population. So first things first, before we can get to the conditions, here is the way that we write the hypothesized line. Okay, we've been using y hat equals a plus bx. When we're talking about the line that fits the entire population, we use the notation mu sub y, and instead of a, we use alpha, and instead of b, we use beta. Now, you just have to get over the fact that alphas show up in different contexts in mathematics and betas show up in different contexts. This is not the same alpha or beta we've seen in other kinds of inference. Okay. All right. So mu sub y equals alpha plus beta. That's the line that's going to fit the entire population. So a is going to approximate alpha, and b is going to approximate beta. And when I put them together, I'm going to get a line called mu sub y. That's the concept here. Now, one other concept I need to talk about for a moment here. And that is, most of the time, we're more interested in trying to figure out how well B approximates beta than we are interested in about how A approximates alpha. Okay, so we're really, most of the time here when we're talking about inference for regression, we're really interested in the slope. We're not terribly interested in the entire line usually, and we're not terribly interested in the y-intercept. Why is that? Well, that's because that if we go back to the cry count example, okay, what this is saying, the 1.49 says that as I increase cry count, I can expect an increase of 1.49 in IQ. That says there is a positive relationship between cry count and IQ. Okay, so the slope means not only a numerical relationship, but it says there is a relationship, and that's what's important about this. The 91.3 simply says that if the cry count is 0, the IQ is 93. As a matter of fact, there are no babies who don't cry at all, so this is not a terribly useful statistic, to tell you the truth. Okay, so trying to approximate the real y-intercept of the line is actually kind of useless. Okay, instead, we're almost always more interested in the relationship between the two than we are about where the relationship begins. Okay, so back to our conditions for inference. So these conditions are maybe a little tricky at first. The first thing is that we need to have independence. We're used to seeing that, so that's just an independence assumption. Is each individual independent of the others? The second thing is the line is a straight line. The real relationship is a straight line. This doesn't work if it turns out that the real relationship is quadratic or exponential. Okay, it has to be that this is a straight line relationship in reality. This is an assumption we must make. Most of the time we do not know when we start out that the original relationship is linear. It's just an assumption we have to make, and there's not much we can do about that. Okay. These last two go together. It says the standard deviation is the same for all values of x. Okay. That is, for any cry count, the variability of IQs is the same from cry count to cry count. So if I have a baby who cries a very little and I have a baby who cries a lot, the variability of the IQs in both those are the same. And moreover, the distribution of the cry count for the small, the distribution of the IQs for this baby who doesn't cry much, and the distribution for the IQ of the baby who cries a lot are normal. Okay. Here's kind of a summary, and this is a nice picture of that concept. Here is a baby who doesn't cry very much, and here's a baby who cries a lot. Okay, we have to assume that the variability of the IQ, it's a lower IQ here than here, but the variability is the same of babies who cry this amount versus this amount, and the distribution is normal for both of those. So the four conditions: independence, truly linear, standard deviations of the same, and normal curve everywhere. Okay. Now we get into the calculation, and the first thing I want to say about this calculations is you don't have to write this down right here, and I will show you what you need to write down. You should have a sense of what this is. The standard error about the least squares line is the variability around the line. And how you do that, you find the sum of the squared residuals, you divide by n minus 2, and you take the square root. This is one of those formulas on the formula sheet that I've said before is not one that you're going to be forced to use actively, but you do need to be aware of what it is. So that's S. That's the variability around the line. Here's the formula for the confidence interval for a regression slope. Okay, so usually what we're trying to do is we're trying to estimate the real slope using the sample slope, the slope we calculate, as an estimate. In the same way we do x bar plus or minus t star times s over the square root of n, now we have b plus or minus t star times this thing called a standard error, okay? And the standard error is our new s that we just saw on the previous page divided by the square root of x minus x bar squared, summed up. Now, again, your head's probably spinning a little bit here. Where in the world are these numbers coming from? Okay, breathe deep because it's okay. We're going to get there, okay? So don't worry too much about this calculation yet, okay? Instead, here's what I want you to think about. It's just a confidence interval. Estimate plus or minus t star, okay, because it's a sample and we don't know the actual standard deviation, times the standard error. Now the only thing that you need to worry about right now is this is a t star. How do we calculate t star? We look in the table, but here we use degrees of freedom for n minus 2. This is two variables, so we have n minus 2. So if I had 38 babies, my degrees of freedom is 36. Okay. So this is a little tricky. So we're going to come back to this to actually calculate it. But let's just go ahead and state that we have a 1.49 is going to be our estimate, plus or minus the t-star value for 36 degrees of freedom, and 95% confidence is going to go here. And then we're going to have to calculate the standard error of the slope. So hang on tight. We're going to figure out a quick way to calculate this shortly. Okay? But now we have a way to calculate a confidence interval. This is going to give us the real value of the slope within a certain margin of error. Hypothesis tests. Okay? Again, same concept here. The only thing that's kind of interesting about this is whenever do a hypothesis test for slopes, the null hypothesis is almost always the slope is 0, and the alternative hypothesis is the slope is either bigger than 0, less than 0, or most commonly not equal to 0. Why? Okay, the simple answer is this says there is no slope. What does that mean? If there's no slope, there's no relationship. So the null hypothesis, another way to look at it is the null hypothesis is, in actuality, there's no relationship between x and y. And the alternative hypothesis is, in actuality, there is a relationship between x and y. So in the case of crying and IQ, it's not entirely clear to me that there would be a relationship between crying and IQ. The thing about it is that anytime you put data into your calculator, you're going to get a slope. Okay? What we might ask now is that slope just due to variability, and we're just seeing the fact that there's always going to be some kind of line? Or is it that if I got all babies, I would end up with a positive slope? That's what I'm asking here. Is it true that the slope I see is due to variability, and in real life the slope is 0? Or is it true that the slope is actually a different number? Okay. Now, here are the three situations. This alternative can be greater than, less than, or not equal to. And you see it's the same pictures we've had in the past. And my test statistic is t. And t is simply the slope we start with divided by that number, the standard error of beta. Again, degrees of freedom is 36. Okay, so now you're probably saying, well, okay, this is not a hard thing to calculate. Okay, in the past we've done like x bar minus mu over s divided by the square root of n. That's kind of tough. This is not hard, except we still can't really get our head around what standard error of beta is. Here we go. I'll show you how this works. 99.9% of the time, when you're asked to do this calculation, you're given the regression analysis. Okay, we've seen these boxes before, where they show you, okay, the relationship is 91.2 plus 1.49 times the cry count, and the 91.2 comes from here. The cry count is right here. And we've seen this many, many times in the past. In the past, though, I've said just look at this and this. Don't worry about the other stuff. Now I'm going to show you what the other stuff is. First of all, that first number s is right here. That was the sum of the square residuals divided by n minus 2 square rooted. It's given to you is the point. Second, the standard error of beta is this number here. It's the standard deviation of the slope. Okay? Standard deviation of the coefficient to the cry count. Okay? Pretty neat, right? So this is SC sub B, this is S. Okay, so if I want to find B plus or minus T star times the standard error of B, I simply have to find B, which is here, and the standard error of B, which is here. All I have to do is find T star with n minus 2 degrees of freedom. Even better, though, if my null hypothesis is this, and my alternative hypothesis is this, and I'm asked to do a hypothesis test, then my test statistic is B over the standard error of B, which we know, B, standard error of B, but lo and behold, that ratio is right here. In our case, it's 3.07. So the test statistic T for the cry count for the slope is 3.07. Even better is that when we're doing a two-sided hypothesis test, the p-value is here. Okay. Do I expect you to be able to do this right away? No. Okay. But what I'm trying to show you is that there's a lot of information buried here, and there's virtually no calculation that has to take place in order to come up with a solution to this problem. So let's go ahead and look at the hypothesis test, okay, and come up with some kind of conclusion. The null hypothesis in this case is that the actual slope is 0, and the alternative is that the actual slope is not 0. We don't know if it's positive or negative, but it's not 0. Okay. That means, in this case, that there would be, if the null hypothesis were true, there would be no relationship between cry count and IQ. The relationship we saw was simply due to random chance. The alternative hypothesis says that the slope is different enough from 0, the slope that we saw is different enough from 0 that it probably didn't occur by chance, and there really is some kind of relationship between crying and IQ. Now, the test statistic here would be 3.07, and the p-value would be 0.004. The p-value is very small, so in a case like this, I would probably say I will reject the null hypothesis because the chance that that happened simply due to chance is exceedingly small. So we would probably say here that we don't know what the real slope is, but we know that there is a positive or negative slope. It's not a 0 slope. Okay? So based on this data, it appears that there is some kind of relationship between crying and IQ level. All right? So that's it. This is the last topic in AP Statistics. Pat yourselves on the back. Thanks for watching.